Hello everyone, I am Adarsh Ranjan from Calsoft and I want to welcome you all for the webinar. We are delighted to have you join us today as we discuss debunking QA myths for flash-based arrays. The webinar will be hosted by Ravindra Singh, Lead Architect, Storage Quality Assurance. Before we start the presentation, I would like to go over a few housekeeping rules. We will have a 40 minutes presentation followed by question and answer session. By default, all the attendees will be on mute. At any time during the webinar, you can use the question window on your panel to ask any questions. If you have joined via phone line, please mute your handset to avoid any disturbance. Also, we request you to view the session in full screen mode for a better webinar experience. Without further delay, let me hand over the platform to Ravindra. Over to you, Ravindra.
Hi everyone. Good morning and good evening. This particular presentation talks about the all-flash array or the flash-based array testing techniques and how should we go about it. So without further delay, let's start with this presentation. So the agenda of this presentation is introduction of the types of flash arrays that are present in the market right now, challenges that we normally face in testing the flash-based arrays. What are the key feature testing, which includes your flash translation layer, garbage collection, discard and map testing, performance testing or performance benchmarking of your all-flash arrays, using synthetic tools like FIO or Ammeter, using enterprise applications like TPC, SPC or MarkLogic, or using a predefined or pre-configured system parameters with basically other parameters and pictures like discard and map. Going forward, we have application testing, what kind of applications are normally tested in Flash and how they are tested, and what are the customer-centric testing scenarios that normally Flash deals with. And lastly, we have a QA metrics, which talks about QA metrics in general. I mean, what are the QA metrics that we target for Flash-based arrays? Moving on to the next slide. This slide basically talks about this slide basically talks about two kinds of flash arrays that are present in market right now. So one of the flash arrays, all flash array, which basically has all the disks as SSDs, and replacing the whole spinning drives from your chassis. The nature of flash storage allows for much faster transfer data rate as compared to traditional spinning disk with their own latency and seek time problem, which are not present in the flash. The other kind of flash arrays are hybrid flash arrays, which are basically a combination of your spinning media plus the SSDs. So it basically adds a thin slice of flash to a storage array, which basically increases IOPS and reduces the read latencies. Moving on to the next slide. So these are typically this slides and the further slide typically are typically portrays the challenges that we have in flash-based array testing. So starting from understanding the key features in Flash, which are basically your flash translation layer, your garbage collection engine, features like discard, unmap, trim, and their impact on performance benchmarking of Flash. And the second point is building an automation framework for testing and continuous integration around this Flash-based arrays, which solves a lot of problem in terms of man-hours. The third thing is customer-centric testing around the all-flash or the flash-based arrays and understanding the right customer and the use cases for customer-centric testing for flash-based arrays. Fourth one is the compliance testing, which we run through flash-based arrays. And the fifth one is the white box array injection kinds of tests that we run on all flash arrays or the flash-based arrays, which includes hybrid and the normal flash-based arrays. So continuing with challenges in flash-based array testing, the biggest challenge that I have personally seen with a lot of array vendors is the performance benchmarking. I mean, how do we performance benchmark our storage array or a flash-based array? What are the best metrics to do that? What are the best tools to do that? And So this basically deals with evaluating tools for performance benchmarking or choosing the right kind of solid state drives, whether it's a MLC, SLC, or enterprise grade solid state drive. So typically SLC behaves better than MLC in terms of read or write performance because the type. So there are so for a given data block, there are only two states maintained in SLC kinds of storage, which are basically 0 and 1, and for MLC kind of SSDs, the data segments ranges from 3 to 16, and which again is a bigger problem to solve, and hence there is a performance impact in such kinds of MLCs. We can go in depth of all these things, but again, this particular slide or presentation is more towards how do we deal with all those flash array based testing things. So let's focus on that for now. So let's see how do we normally do a performance measurement or performance benchmarking in flash-based arrays. So to do that, we need to follow a set of steps which are basically mentioned in the IDC docs of flash performance benchmarking, or there are various other links where it is mentioned. Just to revive on those, so there is the first point is create a common starting point. I mean, you need to have a solid state storage at a common starting point. Normally, that common starting point is the out of the box or the fresh flash-based storage array. You can achieve the same common point by basically performing a low-level format on the SSD or to secure wipe the SSDs every time when you take a performance benchmarking. The second state that we move to is conditioning. So a FOB or a flash out of the box kind of array normally performs way better initially as compared to when you write to that more and more because of various issues like leveling or write amplification. So it's better to have a steady state or a conditioning state done to your flash based storage before taking the performance numbers. So these numbers shouldn't be reported as a demonstration of the solid state true sustained performance when we are taking directly from the out of the box flash array. So typically we need to run a random 4 KB or 8 KB writes run against your storage for approximately 90 to 120 minutes, and it again depends upon the manufacturer, the transfer size or the amount of time needed for conditioning. The third state that we need to go through is a steady state. So basically, performance levels is settled down to a sustainable rate. That's the performance level that we should report as part of our array's performance numbers. The fourth, and I would say one of the most important step is reporting. So this level of reporting is very, very important. I mean, if a standard benchmark requiring full disclosure wasn't used, there is a minimum amount of information required which needs to be reported. Like typically, what kind of IO load was it? I mean, and what are the block sizes that we are running this IO load with? With solid state storage, most random write workloads don't perform any better than performance that HDD system yields. Again, this deals with the issues like write amplification. I mean, because of write amplification, the writes are normally as par with the HDD in most of the cases, depending upon the FTL kind of algorithm that vendor implements for handling these write amplification issues. The better the algorithm, the write latency is, and the better is the write performance. So these are typically the steps that we need to perform before taking a flash-based array performance. Then apart from that, there are things like stress realistic emulations of typical supported workloads, like having your real world environment to be run on flash, or real workload like your database workload, your application workload running. Apart from that, having stress your array to a certain level with features like snapshot, consistency group, failover, application backups, and taking the performance in parallel, and how does an array behave at that point in time is again something to measure, because this may not be your publishing result, but this gives you a confidence how array performance will get impacted with all these areas. Moving on to the next slide. Basically this deals with key features, which is basically introduction and testing of your Flash-based features. So Flash-based array consists of basically a Flash translation layer, which is normally written at the controller as a software layer. This FTL or a block translation layer normally maps the LBAs from file system to PBAs of your solid state devices, and basically it has this logical to physical block addressing. Normally, a Flash vendor implements a write amplification reducing algorithm, which I have already covered in the previous slides. So there has to be a write amplification reducing algorithm to have the better write performance in picture. There has to be a wear leveling engine written on the FTL to have the better wear leveling addressed. So we'll talk about wear leveling in future slides. Then there is a garbage collection algorithm and policies, which normally a Flash vendor writes into their own FTL layer. So this deals with how a garbage collection on FTL will behave, and what are the kicking time of those garbage collection engine, like when it should kick in, and what is the particular time to kick in that particular garbage collection engine, because unnecessary running of garbage collection engine can impact the performance in a worse way. And then we have a bad block management engine written inside FTL to manage all the bad blocks which are coming through the cycles of write on your Flash-based storage. And then protection against power loss is again case-to-case kind of feature that all Flash array implements or a Flash-based array implements. It basically deals with storing the in-memory or in-flight IOs into a battery backed up or a capacitor backed up card, and basically replaying that in case of disaster through the card to basically protect the in-flight or in-memory IO. So FTLs, again, as I said, FTLs can be implemented at different levels. So normally a couple of Flash vendors implement them at a Flash array level and at a controller level as a software, or this again can be implemented at a SSD or a Flash drive level. So moving on to the next slide. Yeah, so these are typically the Flash translation layer testing areas, which includes write amplification. As I've already talked, we need to touch write amplification because this is kind of a feature which normally all Flash vendors implement in their FTL layer, because this is something which is causing a real performance impact on a lot of Flash arrays as of now, and people are handling this particular issues with their own ways of algos. Then we have a typical data integrity test, which basically runs on your FTL layer using either your file system layer through initiators or directly writing to your FTL layer using tools like FIO, iMeter, or DD, or some kind of data integrity tool. Features like deduplication and compression. So again, these are again FTL based features which normally gets targeted by a lot of vendors now, just to have better feature matrices and storage arrays, and these are basically inherited from the normal HDD or the HDD based or STD based arrays. So for a typical deduplication testing, normally people use tools like btest and all to test the kind of deduplication the Flash array or the array supports. Then we have load, stress, and scalability. So there are different tools for all these areas to test on. So for a load, you can always have customer-centric tool like VDI using login VSI, or having your MSCS or Hyper-V kind of workloads running, or having your ESXi clusters running over your all Flash arrays and stressing it with a lot of VMIOs or the normal IOPS. Again, the scalability deals with testing large clusters on your all-flash arrays, which again deals with MACS, Hyper-V, ESXi, or the VDI kind of stuff. Then testing the boundary conditions is very important. So boundary conditions or run-to-fail conditions are those conditions wherein we need to check how a flash will behave when it really reaches to its boundary. I mean, the boundary could be the device fill or very small high rate IOs, or creation of large number of LUNs on a particular all flash array, and how does a flash array behaves at that point in time is something that we need to test before delivering the flash array to market. Then the other area is performance of FTL. Again, this could be covered in later slides, but just to give a gist of that performance is, you can always have this performance testing running using performance tools like VDBench, IOmeter, FIO running directly over FTL or through the initiators with different configurations. Like you can have your LVM carved out couple of LUNs over your FTL and exporting those LUNs to your initiators and running IOs from initiators on those LUNs using different tools and getting the performance from the initiators. The other areas that we need to focus on FTL is white box testing or array injection testing. So these are all synthetic tests that needs to be present in any software that we normally write. But here it is almost as equivalent as other softwares, because these tools tends to get you the issues or the bugs way early in the cycle as compared to later, and that's how you can really get the bugs which are part of your development phase early in the cycles. And then the biggest add-on is running a static code analyzer like Coverty Coverty or CLang or LCOW. But these tools are very solid to prove or to check the untested or the dead parts of the code way before in the cycle. And the reports on these tools are so wide and so well proven that you can almost fix everything which deals with dead code on your code. So way early in the cycle. So moving on to the next slide, it is garbage collection. So garbage collection is basically a process by which SSD manages the dead or half-filled write blocks on your desks. So this basically deals with identifying partially filled valid data in cells and collate them, rewrite them to a new cell, and delete them or reclaim the freed cells for a new write. So normally your garbage collection runs at two different levels on your flash-based arrays. As I've already told, a lot of vendors implement that in their FTL or the controller logic. But nowadays there are SSDs which are coming with this garbage collection engine inbuilt in a firmware. So basically it increases the write performance by making free cells available, and reduces the wear leveling by enabling erase cycles. So basically wear leveling deals with a process that is designed to extend the life of your storage devices. So normally a storage block or a cell has a finite number of program or erase cycles before it really becomes unreliable. So for example, a single cell NAND flash is typically rated at about 100,000 program erase cycle. So wear leveling is an engine which basically arranges data so that write erase cycles are distributed evenly among all the blocks or all the cells in the device. So this is again something that has to do with the kind of implementation that particular vendor has. So wear leveling normally goes into two different categories, which are dynamic and static wear leveling. And just to give you a gist of it, dynamic wear leveling basically pools erase blocks and basically selects the block with the lowest erase counts for next write. And static wear leveling basically selects target block with the lowest overall erase count and erases the block if necessary. Write new data to the block and ensures that block of static data are moved when their block erase count is below a certain threshold. Moving on to the next slide. So this is typically a pictorial view of a garbage collection working. I mean, you have your on disk divided into different chunks or blocks of data, as in the before strip you can see, and then the after strip is basically when the garbage collection gets kicked in. It basically collate all the on disk write blocks to a single blocks to a continuous block of segments, and those can be used by the other writes which are coming later in the cycle. Moving on to the next slide. So basically a garbage collection. So this slide describes how to test a garbage collection engine. So again, the primary goal is the functionality test. Whatever your garbage collection engine or algorithm says as part of your design, which is HLD or LLD, you have to test all those features. Plus, if there is another functionality that you want to add to your garbage collection engine, then the second point could be performance impact using automation. Now, the performance is one of the biggest area of concern for garbage collection and the normal read and write IOPS. So whenever you have a read and write IOPS performance going on, if the garbage collection gets kicked in, what is the performance, overall performance of your array is something that any flash vendor or storage vendor should measure, because this can give you an impactful result in a scenarios wherein you're basically writing a lot of data to your array, and your garbage collection engine gets kicked in and tries to free up the half-filled or the unused kind of write blocks from your disks and try to remap them for the new writes which are coming. So this basically gets for this particular garbage collection engines to get kicked in, it basically will use the cores of the CPU. There has to be different threads that needs to be spawned, and all these things will basically choke up the CPU cores which normal read and write IOPS are using at that time. So it's very important to have this kind of performance measurement to have this confidence of behavior of your flash-based storage in such scenarios. So I've already discussed the change in configured number of threads. You can always change the garbage collection threads depending upon the kind of performance you are targeting. It could be more or less impact such situation like disk fill and heavy discards, how your garbage collection engine is taking all those things into consideration. Testing and tuning garbage collection kick on and off time. So this is again a very important factor. I mean, normally the way people work on these engines is they have this static or a hard-coded time wherein you say if my whole flash array is filled up with 70% of data, I'll kick off the garbage collection engine just to check if there are these write blocks which are half filled or partially filled. I can empty up and create a bigger chunk of free write blocks for the newer writes. That's where the garbage collection engine gets kicked in. And then there is a write blocks based garbage collection engine kicking time too. I mean, you can always have X amount of write blocks are partially filled, say 50% filled, please kick off the garbage collection engine. So these are the algorithms that you can maintain. But these are again always a time bound algorithms wherein you have to have certain conditions met before it gets kicked in. And you can always have these things configured through a proc to get kicked in through a user while testing. Okay, but there are other kinds of garbage collection algorithms too, which will basically automatically get triggered and will keep on working in the background when there are IOs coming or read or write IOs coming from the initiators. So let's not go into depth of all these things. Let's cover here, and based on the questions, we can answer those things. Then again, there is continuous heavy IO and impact on write performance that we can test on the garbage collection testing. Moving on to the next slide. So discard and map trim. This is basically an interesting problem that solid state devices normally facing, and it has been in this industry since the birth of solid state devices. So basically, a discard command allows an operating system to inform solid state drive which data blocks are no longer in use. So typically, the way the SSD behaves is when you say through a file system that I'm deleting this particular LUN or particular LBAs, it goes into, it basically marks those LBAs as unused or dirty in below on your FTL layer, but it doesn't delete them or it doesn't zero out them. So this is a typical problem that happens in this card Unmap, and SSD vendor has to explicitly go and delete all these things, and doing this is basically taking some amount of bandwidth from your normal FTL engine. And to basically consider or to basically avoid such situation, we have discard and map and trim implementation. So there are two different kinds of discards normally. One is the normal discard, which deals with don't care read output for discard blocks, and the second was a secure, which basically ensures that it zeroed out all the LBAs or data blocks which are normally thrown from the discard command. So discard is used in an opportunity to trim the data blocks on the SSDs. So basically, what is the big deal with discard? I mean, what is the big deal with trim? So trimming basically enables your garbage collection engine overhead. Basically, it reduces the garbage collection engine's overhead because you have already a couple of data blocks or write blocks which are already discarded or trimmed and given to you, and garbage collection engine doesn't have to work there. So otherwise, it will significantly slows down the future write operations, because garbage collection engine will kick in and it will try its own logic to free up the blocks or discard the blocks. So the second thing is enable better array cycles, increasing lifespan of SSDs. So it basically helps in doing the wear leveling for the SSDs. So SCSI command set normally provides unmap command, which is full analog of trim. Moving to next slide. The next slide deals with how to test the discard unmap. So the typical and the easiest way of doing it is enabling this in Windows, and you can always have a command in Windows to check whether the particular block, particular drive or block is discard enable or not, and you can have discard or trim. Trim is fired from Windows initiators and check whether the trim commands are coming to your flash-based storage and doing their work or not. You can always have tools like AFA meter running and while deleting LUN or directly writing zeros onto your FTL. So the other area to test on is the performance impact because of discard or trim. So impact on IO while discard and map in progress is something to test on while calculating the performance using configured parameters. Again, while cert is loaded, stress with IOs, verify that discard performance is not getting impacted. So discard performance is another paradigm where people normally publish their results on discards. Like so for a naive user or third party user, the way discard performance are shown or published is this is the time I'll take to delete a particular LUN. Okay, so this is a discard performance, and this is again published by a lot of vendors. So this is something to test on too, and with different kinds of load or just the discard going into the picture. So yeah, we can move to a new slide. So this is something that is pinching, or that is the basic problematic area for a lot of flash vendors right now, which is performance testing. I mean, how do I measure performance? Because to me, flash are built for performance. I mean, performance. Flash gives you better performance as compared to your normal HDD based spinning disks. Apart from performance, there are other good features like it reduces your power, it reduces the noise that hard disks makes. But performance is one of the major areas that people are dealing with flash, and that's why flash into the market. So let's move on to the next slide and discuss about performance. So normally, as we have described in our first slide, so we have performance measurement in three categories divided here. One is using the load, the synthetic tools. The second is the enterprise tools, and the third one is the configured parameters. So So covering the first one, so synthetic tools are basically called as load generators because they typically generate a load. So load generator is a tool used to simulate a desired load and help reveal performance issues. These are typically the kind of tools or generators which are used early in the phase of development cycle of your all flash array, which gives you a confidence like my particular flash array behaves so good with such operations using different tools like FIO, VD bench, or imeter. So you can always have a full automation of such tools or a single click automation of such tools, which basically runs the performance numbers on. It basically creates a setup for you with different paths. I mean, if I take example, typically you can have FTL, LVM running over your FTL, exporting couple of LUNs to your initiators, couple of initiators having multiple paths configured to them, and running a particular workload using FI or imeter or VD bench on those initiators, and then publishing the result back to user in forms of CSVs or XLS. So all the flow that I talked about is fully automated and can be done using a single click automation. I mean, you can have a configuration file somewhere present. You can just tweak the configuration file, run this particular test suite, which will basically do the setup for you and run the IO for a given amount of time with different threads or block sizes, whatever you have in configuration, and get the result published for you. And this really helps in reducing the time wherein people normally spend a lot of time doing such things in their normal test cycles or dev cycles, wherein they typically prepare the setup manually and run all these tests manually and get the result and then analyze them. You can actually have an analyzer tool also automated in all these scenarios, which will give you all the results for every build to build or every alternate build, depending upon the way you want to run it in your sanity or nightly environment. So again, these tools deals with adjusting the knobs. When I say knobs are basically adjusting the configuration parameters like your read-write threads, your queue depth, your block size, and all these things to simulate certain types of workloads. So this is basically a load generator and performance using synthetic tools slide. We can always have a B-test kind of tool which will basically generate a lot of deduplication data, and we can always measure the performance of deduplication using such tools running on your flash-based arrays. So moving on to the next slide. Now, this is something that industry is typically moving towards. I mean, the first slide that I covered is typically industry is in the flash-based arrays or vendors are basically aligned to because they have their own set of performance tuned parameters which they can easily tweak in synthetic tools and publish the result, wherein they can say supposedly like 4K read write 50%, 4K block size 50% read write IOs are behaving in such a manner with this tool with such configurations. But as we progress more, the customers are becoming more intelligent, and there are third-party vendors which are coming as a savior to customer, wherein they say, okay, we're gonna measure the flash performance for you guys, or we can be a standard body which can measure the flash performance for any flash vendors. So those are typically the ones which are called benchmarking vendors or benchmarking tools which they use. So a benchmarking normally is defined as a workload and measurement methodology which does not change the characteristics. Okay, and standard body which offers such benchmarkings are SPC, SPC, or SNIA SSI, triple SI. So the normal storage benchmarks that these guys runs are TPC, SPC 1.2, Mark Logic, SpecFS, and all. So the type of workload that these guys produces while doing a benchmarking of your SSDs are OLTP workload characteristics similar to an Exchange or a messaging server, or a distinct workload like large file processing, video on demand, large database query, etc. And for this kind of scenarios, it basically simulates request handling capabilities of file servers using file share protocols like NFS v3 and SIFs. So these are very important benchmarking tools as per the customer's requirement is, because these basically generates the real world workload simulations for you. So as I said, I mean, you can easily generate a large file processing or video on demand kind of workload using these tools. And video on demand and large file processing are something that is being heavily used in industry for all flash arrays. So a customer or third party normally should get array which gets certified using all these standard bodies with particular numbers of IOPS or throughput. Moving on to the next slide. This is something that normally a lot of people don't cover in my experience, but this is very, very important paradigm of measuring the flash performance. So this deals with everything that I talked previously on other slides, plus there are other things like, people don't publish their, for example, people don't publish their unaligned IO performance using tools like FIO or IMeter. I mean, or any unaligned application like VMware, bootstrapping or something like that, which produces a lot of unaligned IO to your underlying flash-based storage. And this is something to be published, and this is something to be tested by a flash vendor before submitting the results on the performance or releasing the product. So typically the unaligned IOs normally ranges from having your sector unaligned IOs from 11K, 9K, 17K or 13K, writing such kind of BS block size on your particular flash array and getting the performance out of it, like how a flash behaves with unaligned IOs. We always know that how it behaves with aligned IOs because those are the results which are published. But in an ideal case scenarios or ideal environment, but how do it behave with unaligned IO is something which is really important. Then the second factor could be the IOPS normally published by vendors are normally 5 and 2 bytes block size aligned, because those are always producing good results or good IOPS number as compared to a 4K or 8K or bigger chunk size of block size, bigger block size IOPS. So basically, what I have seen and what I have read in IDCs and in different papers is with change of number of in the block size from 4K or 8K, the IOPS drops by 20 to 40% depending upon the kind of algorithm that a particular flash vendor has implemented. So the kind of IOPS that normally we get in industry or in customer environments are basically in Ks instead of bytes. So it's very important that we run such kind of block size with the flash before confirming the IOPS published by the flash vendors. The other area could be with changed number of threads and features in place and having the performance measurement. As I've already discussed, having a disk going on along with your normal write IOs or read IOs and taking the performance at that point in time. This could be an impactful performance number which might not be there in the published result. Then we can have change number of read-write threads or RAID chunk size or BS size to check the performance tuning. We can always have different. So we can always have the garbage collection engine kicked in at the time of performance and see what is the performance at that point in time. So these are all pre-configured or configured or changed kind of parameters that we can always run through while taking performance to see how a flash behaves in extreme conditions like disk fill conditions and all, which will be what the flash vendor normally publish in their results or PRDs. So so moving on to the next slide. This particular slide consists of application testing that we normally perform on our flash-based arrays. So a normal flash-based array is typically best for I/O or data-intensive application, as it has better IOPS as compared to traditional HDD-based storage system. So typical application that we run on flash-based storage are database application, which really required IOPS to be faster, which ranges from Oracle database to MS SQL, DB2, or clustering application like MSCS, Hyper-V, or ESXi clusters, applications at a enterprise level like SAP and all, or the one area where I have seen Flash behaving really good is NoSQL databases like Membase and CouchDB etc. And the last area that Flash is basically behaving very well because of read reduced latency is applications like audio, video, and image editing software. Moving on to the next slide. This slide basically covers the customer-centric testing that we run through typical Flash-based arrays. So these are not very different than what we run on a spinning media or HDD-based arrays, but these are very important to basically certify or basically say that a Flash array behaves equally or better than a HDD media-based array in industry. So having a simulation of customer environments in place before the release of a product is something that every Flash vendor should do just to avoid last-minute surprises at customer environment. And I've seen a lot of people not doing it, but this is something needs to be covered either in the beta phase of the product or before the first customer shipment. So these areas basically deals with having AFA clusters and features running like snapshot, clone, etc. Having the certifications of these things running like the VS, the Windows vehicle certifications running way before the release. Having VDI tests running, which is basically a normal workload, a use case right now in a lot of customer environments for Flash, because Flash is good for read and read-intensive workload, and this is where it is helping out a lot of customers to deploy large-scale VDI clusters or VDI nodes onto your Flash-based arrays. So a typical production use case is basically having Bootstorm running for 2,000 plus VMs or 3,000 VMs using VDI with VI on and off on a Flash-based array. Then again, different other workloads are like MACS and Hyper-V clusters and its features. Centric and VMware Horizon, which is already covered, it's a part of VDI, which people run on the Flash-based storage. As it is a read-intensive I/O going on in these areas, it really benefits the user because Flash has a better read-intensive I/O as compared to the HDD or the spinning media. Then we have a typical building production hardware configuration to test. This is something that is dependent upon use case to use case. This is basically deals with having a maximum number of paths by having multiple FCI SCSI switches with a matrix of connections. I mean, you can have like ranging from 64 to 192 paths to your Flash arrays, which are basically FC connection paths, having couple of MDSs in between and simulating the real workload, real customer workload from top to bottom. From top, you can always cluster or the database application, and in between, you can always have such configurations which simulates the HA kind of stuff for a lot of fiber channel or path related work, and then you can have IOPS running on your Flash-based arrays. Moving on to the next slide. I think that would be a last slide for us. It basically deals with the QA matrices. So normally, typically, the QA matrices produced by a lot of storage vendors or vendors across testing areas have defined set of QA matrices. So these, the areas that are mentioned here, to me are plus to that particular list. I mean, that particular list being a constant, these are the plus areas that we need to really focus on while testing such scenarios or such Flash-based storage or any storage system. So, which deals with how many number of test cases you have written, what is basically a test case density for your code, like how many tests per KLOC you have written for your code or your product or your feature. What is the code coverage? You can always have QWERTY, LCOV, GCOV, or any static tool code coverage and analyzer like your CLang or your Purify to run on your code to test the code coverage. You need to measure the defect density to have a confidence on the code path that is being tested. Then again, what is the automation coverage? This is something which is really important personally to me, because it gives you a confidence of your code being solid, and it reduces a lot of cycles for you to test your code with. And the last part is, what is the count for error injection error and white box kind of testing error. This can very well be clubbed with the code coverage tools that we have talked about earlier. So I think this is pretty much it. This is what I wanted to present to you guys. If you guys have any questions, issues, queries, you can shoot, and let's see where we are. Thank you.
Thanks, Ravindra. Now we will discuss any questions you may have regarding the webinar. If anyone has any questions, please type them in your questions window in the panel on your screen. Ravindra, we have a question. Any memory leak detection tests? Can you share your thoughts on that?
Yeah, we can always have memory leak detection test. I mean, Sriram, was it you?
So there are different tools which are already available, like Valgrind or standard tools which can be used to detect memory leaks and stuff. Certainly, like on the kernel components which are developed, it's not such a straightforward job. So typically, we at our end would recommend something like in your memory management logic itself, have sufficient amount of hooks and information which gives the information about any kind of memory leaks. So which would be typically identified when you're like removing your modules and stuff, and then the kernel would report that these are the kind of amount of memory leaks that we are seeing up. So there are different tools, and typically if you're getting into the kernel space, then there is a standard way of doing it, and it's by having a wrapper over your memory management.
I agree with Sriram, and typically the tools like Valgrind and all helps, but having this implemented in your kernel stuff always helps out. I mean, a typical answer to the question could be, you can always have the driver usage in place, or your free kind of which is inbuilt Linux tool to have in place and running while your module is running into the picture, and you see what is the amount of memory it is going through. I mean, how much it is fluctuating while the usage of that particular module. So that could be one of the area that we can test this through. So before going forward, I totally agree with the L. Rosenthal, if I have pronounced it right. I mean, you should mention, so he has asked this thing, you should mention load dynamics, as it is much easier to use and automates the entire. I totally agree with you. I mean, this is something that I haven't mentioned this intentionally here, because again, load dynamics comes with its own price, correct? I mean, and my focus of delivering this particular webinar was not to focus more on the tools which are like really proprietary or which have cost associated with it, but yeah, I totally agree with you. Load dynamics is something which is like really powerful and which can really automate things for you. I totally agree with you.
Okay. So Ravindra, we have another question. We're testing how and who does it? Is it done by the manufacturer?
No. So it can be done by so yeah, again, it can be done by manufacturer, or it can be done by third party, which manufacturing is outsourcing to. But typically, this should be tested by a manufacturer. I mean, Sriram, if you have anything else, you can add here. Sorry. So manufacturer plus the one who is writing the FTL layer. I mean, the controller layer over it, because those are the best guys who can test it through software. I mean, how your SSD wear leveling is going through with different writes and read cycles. Sriram, please correct me.
Yeah, there was another question on similar lines, so I'll just club it together. Like, typically the SSDs or flash drives do come up with like smart capabilities, and there are tools and software mechanisms to get information about these capabilities, or matrices of the SSD in terms of like it could be performance, it could be wear leveling, the erase cycles, or the write amplification that is being seen. So all these capabilities provided by the drives should be really exploited through different tools, like maybe it could be IO meter, or there are other tools too, and then based on that you can really gauge what is the write amplification reduction that is happening due to the FTL layer that you have implemented in your array actually.
So, Ravindra, we have another question. Sure, it's what's the optimal drop-in performance when there are unaligned IOPS?
Okay. So, I mean, it again depends upon the kind of implementation that a particular vendor has. There is no specific answer to it, but what we have seen is, Srinam, please correct me here, okay? And what with unaligned IOs in one of the typical case wherein there's VMware workload going on, we saw a drop in performance somewhere around 30-35% with the normal IOPS, as compared to normal IOPS. But you cannot basically measure it unless it's a vendor specific thing. It basically deals with how you have implemented your own FTL.
Yeah, certainly this is a really good concern, and this needs to be addressed in the design as such. Unaligned IOs really test your array implementations or design, and as far as possible, they should not really degrade below a certain degree, and it also depends on, essentially depends on the design and the implementation, but certainly these should be realistic drops.
Realistic in the sense somewhere around 5 to 10%, but not more than that, because once we had that issue fixed, the drop was somewhere around 5% or less.
Okay. Can you share your views on customer-centric testing, why it is important?
Yeah, I mean, certainly. I mean, to me, it's one of the most important points because, you don't know what beast you are dealing with at the end of the day, because the customers can deploy your product in any ways. I mean, depending upon the kind of PRD you guys have written for it. I mean, you can have your deployment in an environment which you haven't tested any time. I mean, suppose, so as I discussed, consider a scenario wherein your particular box is being used in a VDI kind of environment where you are deploying like 3,000 or 4,000 VMs, but what you have tested is in a simple environment at your test lab wherein you were doing a couple of like 20-30 VMs power on power off or migration, which normally doesn't bombard your storage arrays with those kind of IO pattern which a normal VDI kind of environment do. The other area could be having multiple paths to your flash-based arrays. I mean, a lot of people implement flash-based arrays with the target mode driver placed in their engine, but how that target mode driver behaves at the end of the day with so many requests coming from many paths is something to test on, because customer is not going to run your product unless until it's a mid-size or a low scale customer. It's not going to run your product with like defined set of initiators. Say I have only 2 initiators always bombarding my IO, bombarding my all flash array for IOPS. What you can have is you can have like 32 to 64 initiators with like many paths just to achieve HA through MDS, bombarding your particular systems. How to nearly scale your flash-based arrays to that level, because ultimately if you don't do that, it's okay if you don't do that, but what you'll have is you'll have issues at customer's environment which you'll have a bigger cycle of fixing and to and fro happening when you hit the issue at the customer environment, as compared to handling these scenarios way early in the cycles. Again, on this I want to say that you can actually not simulate whatever the customer is doing every time, but at least you can have some part of its simulations already in present. And I have seen products which are way hit in industry doing or applying such kind of scenarios before releasing FCS to customer. To give an example, Veritas does that. It used to do that. and it's, I believe it's as a tester, as a test architect, I believe it's a good way of doing it. Otherwise, you'll have issues in the market which you haven't uncovered in testing, and this has a bigger cycle as compared to verifying or testing it early. And then again, there is this another angle to it. You can always say that I have verified my storage array with this kind of configuration, which gives you a confidence, and more customers can be approaching you on those areas.
Okay, so another question: what are the typical stats that are necessary to note down while doing performance testing? Very specific to SSDs and not in general to performance testing.
Yeah, so I think I covered this. So the very specific stats could be your IOPS, your latency, your throughput, your block size. All these, I mean, these three could be, I would say, the most important one to note down while doing a testing. I mean, performance testing for SSD.
Yeah,
Sriram, do you have anything else to add? Yeah.
Yeah, just to add to it, if you can get stats almost to the level of like the amount of erase cycles that are being triggered, or how busy is your GC and FTL logic, is something that should be really noted. If there are any mechanisms as something like the smart capabilities can give, then do certainly have a check on those and figure out the performance of your FTL or GC logic channel.
Yeah, basically it reduces the other parties which are involved in doing the performance testing. I mean, it will give you a culprit which may be you or the other parties if you are taking performance from initiators or so. So I agree with Sriram. Or the other things could be wear and tear level. It's not a performance area, but again, you can have those numbers and pictures too.
Okay. So this would be our last question. As most of the SSD vendors have garbage collector inbuilt in FTL, then why some companies are trying to build their own? What more optimization is done here?
Let me just take over this question. It's essentially like when an SSD vendor is building his FTL or his VC engine into the firmware of the drive, he's really limited with the amount of resources. It could be the memory that is available, or RAM available out there, or the processing capabilities that are available out there. While when an array vendor actually implements this, he has a much more wider view. Like he's not just seeing at one particular SSD, but he's looking at a bunch of SSDs, and he can start optimizing at a much higher level, like trying to throw down IOs which are really much huge size. Typically SSDs work really well on write performance with really high size of IO, like at least like half MB and multiple per drive actually. So let's imagine like a case of you have 20 disks or 20 SSDs in your backend or JBOD, and here the FTL, if it is implemented at the array level, it can really consume all of them by sending down really huge IOs as big as like 20 or 40 MB in a single request. Thus, it can really collate and keep IOs coming from the initiators in memory for some while, and then send down a huge chunk. And this reduces the wear leveling and also helps the FTL or DC logic that is also running on the SSD actually. So it makes a certainly a big difference, and you can do other different things as well. Like if you have to really implement deduplication or compression or encryption, it's really difficult to push into the firmware. But if you have your own FTL and GC logic, it becomes really much more easy to implement, and also it gives you always the flexibility of putting the switches on and off as per the requirement. So I think it certainly makes a difference. apart from the SSD drives FTL and GC.
Okay, great. So that ends our webinar. Thank you, Ravindra, and thank you everyone for taking the time to join us today. We hope you find the session really valuable. We would greatly appreciate any feedback you may have to help us improve the webcast experience. Please look out for our email with the webcast recording and the presentation. Goodbye and have a great day.
I would like to add one more thing here. I mean, if anybody has other questions, they can always shoot an email. I mean, this was a small discussion that we had here, but there is a lot more to it that I have personally implemented and worked on, and I can help resolving the queries, or Shriram can help resolving the queries. So if there are more queries, you can personally email to us. I mean, our email IDs are already there in the webcast,
sure.
And if there are any issues and concerns, let us know. Thanks. Great. Thanks, everyone. Thanks, Shriram.
Great. Thank you. Bye-bye.